All right, as promised, I'm going to give you guys a couple more equilibrium problem examples so that way you guys know how to do them for the homework, the quiz, and the exam. All right, starting on slide 21, here's the example. For a synthesis of nitrogen monoxide, where we combine nitrogen and oxygen gases, we use 2 moles of nitrogen and 4 moles of oxygen, and we mix them in a 2-liter flask. If our equilibrium constant is 5.75 times 10 to the first, let's calculate the concentrations at equilibrium. All right, so the very first thing that we're going to do following those steps that we talked about in the last video is we're going to write our chemical reaction for this process. Okay, we're mixing nitrogen gas, so N2 gas, with oxygen gas, O2 gas, and we form an equilibrium where we produce nitrogen monoxide gas, all right? Then we need to balance our equation. We have 2 nitrogens, all right? So we need 2 over here, right? And we have 2 oxygens, so it's balanced. So that's our balanced equation, all right? The very next step is going to be to write our equilibrium expression, okay? Now, our equilibrium expression is just the symbolic form of our equilibrium constant, KEQ. So we say KEQ is equal to, and symbolically, right, we can use our equation up above. We say, okay, well, that's going to be our concentration of NO at equilibrium squared, right, using our stoichiometric coefficient. Then we put that over, right, because we're taking products over reactants. We are going to put that over N2 gas to the first, its stoichiometric coefficient. And then we're going to have oxygen, O2, to the first. Okay, both of these are at equilibrium, okay, because we have an equilibrium constant. All right, now, once we've written that, all right, I do also want to point out that our equilibrium constant, we've got that value from the problem statement, so we can easily write that down here as 5.75 times 10 to the first. Okay, so whatever concentrations we have at equilibrium, right, those are going to be equal to 5.75. Right, now, here for step 3, right, we're going to list our initial concentrations. Okay, now, I've given you moles and the volume of the flask, which means that you can calculate your molarity, right? We know that molarity is equal to moles over your volume in liters, right? So if I wanted my concentration or my molarity of nitrogen, or of nitrogen, N2 gas, right? Initially, right, because those are my initial concentrations, then my concentration of N2 initially is going to be my moles of N2, so 2 moles for every 2 liters, because we put it in a 2-liter container, which means that my concentration is 1 molar, right? Similarly, right, we can get our concentration of O2 initially, and we started out with 4 moles in that same 2 liters, which means that we have 4 over 2, which is 2 molar, okay? And one more concentration that I want to point out is that we need our concentration of NO, okay? Now, my concentration of NO is what initially? Well, I started out with none of it, right? Because I haven't made any yet. So we know that that, if I didn't give it to you, is going to be 0. All right, so now that I've got my 3 concentrations, now I can calculate my reaction quotient, okay, as well as determine the shift, okay? So we calculate Q the exact same way that we calculate K, except we use our initial concentrations rather than our equilibrium concentrations, okay? So Q, right, is equal to my concentration of NO initially squared all over my concentration of nitrogen initially to the first and my concentration of oxygen initially to the first, again using my stoichiometric coefficients from my reaction, okay? Plugging in the values that I have, well, my initial concentration of nitrogen monoxide is 0, right? And I could plug in those other numbers, or I could just realize that overall that 0 squared over some numbers, which is going to be 0. Well, that means that Q is less than my KEQ, which means that my shift is to the right or to products. Okay? And that should sort of make sense, right? If we started out with a bunch of kids in this classroom, right, and none in this one, then we're going to want to shift to the right to kind of balance out the equilibrium. Okay? Now, our next step is going to be our ice table. Okay? Now, part A is to write our reaction. Okay, so the very first thing we're going to do in building our ice table is to write our reaction, which is N2 plus O2 in equilibrium with 2 NO. All right? Now, we have 3 rows, I, C, E. Right? And then we have a column for each species in our reaction. All right? Now, part B is to put in our initial concentrations. Okay, well, we already have those. So we know our initial concentration of N2, that was 1 molar. We have our initial concentration of O2, that was 2 molar, right? And we have our initial concentration of NO, which was 0 molar, all right? Then in step C, right, we write our stoichiometry times our change, okay? So we have our stoichiometric coefficient of N2, that's 1, and we multiply it by the change. Since it is a reactant, or on the left side of our arrows, it gets a negative x. So it's 1 times negative x. Here, we have our stoichiometric coefficient 1. It's a reactant, negative x. Okay, so it's 1 times negative x. Over here, our stoichiometric coefficient is 2. So we have 2. And since it is a product, it's on the right side of that arrow. Since it's a product, it gets a plus x. All right? So now, in step D, right, we take and write our results at equilibrium, okay? So that's going to be the sum of these 2 rows. So we've got 1 molar plus 1 times negative x, so 1 minus x, right? Then we have 2 plus 1 times negative x, which is 2 minus x. Then we have 0 plus 2 times positive x, so that's 0 plus 2x. Well, 0 plus 2x is just 2x. Okay, so then in part 6, right, now that we have our equilibrium concentrations, we can build our KEQ because these are using our equilibrium concentrations. Okay, so next we're going to evaluate into KEQ and solve for x. Okay, so we know that KEQ is equal to our concentration of NO at equilibrium squared over my concentration of N2 at equilibrium to the first, and my concentration of O2 at equilibrium to the first. I know that I want my concentration of NO at equilibrium, my concentration of NO, so I'm in my NO column, and I'm in my equilibrium row, that is 2x, and I raise it to my stoichiometric coefficient of 2, all right? Then I divide that by my concentration of N2 at equilibrium, so I've got N2 in my equilibrium row, that's 1 minus x, and I raise that to its stoichiometric coefficient of 1. Then I need my concentration of O2 at equilibrium, which is 2 minus x, raised to its stoichiometric coefficient of 1, all right? Which means that I have that 4x squared, right, 2x total squared is 4x squared all over 1 minus x times, which if I go all the way through and cross and do the FOIL, right, that's 2, right? So that would be first. Then I do my outer, right? So I have a negative 1x plus a negative 2x, which gives me a negative 3x. And then my last is plus x squared. So that's in the denominator. All right. Now, I also know that my KEQ is equal to 5.7 times 10 to the first. All right. So that means that this is equal to 5.75 times 10 to the first. Okay. So now I'm going to solve this for x. Okay. So what I'm going to do, cross multiply. Right? I'm going to erase this part. All right, so I have 4x squared on one side, and then I take my denominator and multiply it by that. So then that is equal to 5.75 times 10 to the first times 2 minus 3x plus x squared. Okay? Now, if I multiply my 57, right, because this is going to be, if I multiply 5.75 times 10 to the first, that number is 57.5. And then if I distribute 57.5 across, then I end up with 57.5 times x squared, right? So I have my x squared minus 172.5x. I got that by multiplying the negative 3 times 57.5, and then plus 115, right? And that's equal to my 4x squared. Okay, now I'm going to pull my 4x squared over to the side, so I'm subtracting 4x squared from both sides. That will give me a 53.75, and then this will be equal to 0. All right, so now I have A, B, and C, right, where I've ordered in decreasing powers of x, right? So I have x squared, x to the first, x to the 0. All right. And one of the comments that you guys wanted was you wanted me to walk you through at least one of how to do those quadratic formula problems. All right, so I'm going to try to do that for you now. Okay, we've got A, B, and C, right? We know that our quadratic formula, right, is that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm literally going to plug in a wherever there's an a. I'm going to plug in b wherever there's a b. And I'm going to plug in c wherever there's a c. All right, so that means that my x is equal to a positive 172.5, right, because it's negative of the negative b. So a negative of the negative 172 is a positive 172, plus or minus the square root of negative 172.5 squared minus 4 times 53.5, right? That was A. And then we multiply that by C, which was 115. Then we divide all of that by 2A, which was 53.5. All right, and that means that we find that x is equal to 2.28 and 0.9417. All right, now notice, right, that if we use x as 2.28, all right, if I subtract 2.28 from 1 or from 2, right, so if I put in 1 minus 2.28, that would give me a negative 1.28. That means that if I got a negative number, when I put it into here for my equilibrium concentrations, I can't have a negative concentration, right? So since I can't have a negative concentration, I know that that number is not a valid solution. That means that this must be a valid solution. Okay, again, that's because I can't subtract a number that's bigger than what I have to start with. Okay, now, so that means that my x is 0.9417. All right, that means that we get our concentrations next at equilibrium. Okay, so if we want our equilibrium concentrations, right, these are our equilibrium concentration expressions. So that means that if I want my concentration of N2 at equilibrium, well, that's going to be 1 minus x. Well, if I put in my value of x, that's 1 minus 0.9417, which means that my concentration is equal to 0.0583 molar. Okay, I also need my concentration of O2 at equilibrium, right? My concentration of O2 at equilibrium is 2 minus x, which is equal to 2 minus 0.9417, which is equal to a 1.0583 molar. Okay, and then I also need my concentration of NO at equilibrium. Okay, my concentration of NO at equilibrium is NO equilibrium, that is 2x, right? If I plug in my value of x, that's 2 times 0.9417, right, which is equal to a 1.883 molar. That means that these are my concentrations at equilibrium for all of my species. All right? That is how you do that first equilibrium problem example. All right, I'll erase this side first. All right. Again, if you guys have questions, feel free to bring them up in the discussion sections or send me an email. All right. One more example for equilibrium constant. This is going to be on slide 22. Okay, and this says at a certain temp, a 1.00 liter flask initially contains 0.298 moles of PCl3 and 8.75 or 8.70 times 10 to the negative third moles of PCl5. All right, now at equilibrium, the system has 2.00 times 10 to the negative third moles of Cl2 in the flask. Now let's calculate the equilibrium concentrations of each species and our KEQ. All right, so this one's a little bit different than the problems that we've done so far. All right, but you're going to follow the same process, and as you go through, you're going to write what you know and try to find what you don't know. Okay, so now the first thing that we do is to write our reaction, which is PCl5 right? And we know that that's going to decompose into PCl3 and Cl2, okay? So this is going to be our equilibrium equation, all right? Now, the next thing is we need our equilibrium expression, right? Our equilibrium expression was just our KSP, or not our KSP, our KEQ, right? And our KEQ was equal to, in this case it looks balanced, so it's going to be our concentration of PCl3 at equilibrium to the first, our concentration of Cl2 at equilibrium to the first, all over our concentration of PCl5 at equilibrium to the first. Again, taking our products over our reactants. Okay? Now, in step 3, we need our initial concentrations, right? Our initial concentrations are, we have a concentration of PCl3 initially, which is equal to, we take the 0.298 over our 1 liter, which is going to give us 0.298 molar. We also have our initial concentration of PCl5, which was equal to 8.7 times 10 to the negative third moles for every 1 liter. So we have 8.70 times 10 to the negative third molar. All right. We didn't say anything about our initial equilibrium, or our initial concentration of Cl2. Okay. Notice, I gave you the equilibrium concentration of Cl2, not the initial one. What is my initial concentration of Cl2? Since I didn't give it to you, and it's an initial concentration, it is going to be 0 molar, right? We didn't have any when we started, okay? Now, step 4, right, was to determine Q, okay? If we were to determine Q, we would take this and we'd say, okay, well, I need my concentration of PCl3 to the first initially, right, because we're using initial concentrations, Cl2 initially to the first, all over my concentration of PCl5 initially to the first, okay? And then you would plug that in and you would compare it to K. All right. Now, we're not asked for Q, so I'm not going to worry too much about that. The next step, right, you guys could do that on your own. The next step is going to be to set up our ice table. All right. So, part A, right, we write in our reaction, which is PCl5 in equilibrium with PCl3 plus Cl2. We have I, C, and E rows. And again, we have columns for each of those species. Okay. So we have B, we're looking at our initial concentrations. We have those. Our initial concentration of PCl5 is 8.70 times 10 to the negative third molar. My concentration of PCl3 was 0.298 molar. Then we have our concentration of Cl2 initially, which was 0 molar. Next, we do our change, right? Our change is going to be our stoichiometric coefficient, 1 times negative x. Since this is on the right side, since these are products, it's going to be our stoichiometric coefficient, 1, times positive x, since it's a product, right? And then we have 1 times positive x, okay? So then, in part D, I add them up. I've got 8.70 times 10 to the negative third minus x. I have 0.298 molar plus x, and I have 0 plus x, so just x, all right? Then in part 6, right, that's when I'm going to set up my equilibrium expression. right? I know that I have my KSB, or not my KSB, my KEQ. Man, I'm jumping ahead. Got my KEQ, okay? And I'm going to set this up by using this expression, right? I know that I have my PCl3 at equilibrium to the first. I've got my Cl2 at equilibrium to the first, all over my concentration of PCl5 at equilibrium to the first. Okay, so I'm going to plug in my, let's see, I've got X. Oh, I'm sorry. I've got 0.298 plus X. That's my concentration of PCl5 or PCl3 to the first. Then I've got my Cl2, which is X to the first, and I divide that by my PCl5 at equilibrium, which was 8.70 times 10 to the negative third minus X to the first. Okay, now that would be my expression for KEQ. All right, at this point, what other piece of information do we know? Well, we also know that at equilibrium, the concentration of Cl2 is 2.0. The concentration of Cl2 at equilibrium is equal to 2.00 times 10 to the negative third molar, right? Because I took the number of moles and divided it by the 1 liter. Okay, so that is my concentration of Cl2 at equilibrium. So that means that this is equal to X. Okay? Well, now that I know what X is, I can plug X into my KEQ expression. So I know that KEQ is equal to, well, actually, before I do that, let me find, so since I know what X is, I can get my equilibrium concentrations. Let's do that first, right? So I have 2, so if I'm looking at my concentration of PCl5 at equilibrium, well, my concentration of PCl5 at equilibrium is 8.7 times 10 to the negative third minus X, right? Well, X is 2.00 times 10 to the negative third molar, okay? Which is going to give me 6.7 times 10 to the negative third molar. Then I also have my concentration of PCl3 at equilibrium. Well, I know that my concentration of PCl3 at equilibrium, PCl3 at equilibrium is 0.298 plus X, right? Well, I know what X is. X happens to be 2.00 times 10 to the negative third molar, right? So when I add that up, I get 0.300 molar. Okay, so now I've got all my equilibrium concentrations, right? All I need left is to get my KEQ. Well, I have all of these, right? So I can get my KEQ is equal to my concentration of PCl3 at equilibrium to the first, my concentration of Cl2 at equilibrium to the first, all over my concentration of PCl5 at equilibrium to the first. Okay, are we doing on time? Oh, we're doing okay. All right, so then I plug in my concentration of PCl3 at equilibrium, which was 0.300 molar, right, to the first. I've got my concentration of Cl2, right, which was 2.00 times 10 to the negative third molar, right? And then to the first, right? And then I divide that by my concentration of PCl5 at equilibrium to the first. PCl5 is 6.7 times 10 to the negative third molar to the first, which means that my KEQ is equal to 0.0896. Again, it's going to have no units because our equilibrium constants don't have units. All right? So those would be how you do examples of our equilibrium type problems. All right? Now, I am going in our next video. It's going to be really short, okay? But I wanted to make sure that we covered all of this in this video, right? Our next video is going to talk about Le Chatelier's principle and shifts in our equilibrium.